theorem of finite abelian groups. Okay, we know what abelian groups are. They're groups where the operation is commutative. We know what finite groups are, groups with a finite number of elements. And fundamental theorem, so it must be something really important. What it is, it's telling you, it's describing all of the possible structures of the isomorphism classes of these things, of finite abelian groups. So you look at the statement of the theorem there, and it says that every such thing, G, so a finite abelian group, is isomorphic to something of the form, some group of the form, it's a direct product of cyclic groups. Direct product of cyclic groups, and each cyclic group is of order a power of a prime. Okay? So we might have one cyclic group which is an order, whose order is a power of a prime. Remember Zn means the cyclic group. Yeah, it's a particular instance of the cyclic group of order n. There's going to be a direct product of that with maybe another one, E2 to an alpha 2, and we may have some finite collection of these. Okay, I'll stick with it. I'll try as much as possible to stick with his notation here. Pn to the alpha n. Okay, something to look for here. Where the p's are our prime numbers, the I are prime, but not necessarily distinct. Okay, we're not claiming that each one is a distinct prime. Not necessarily distinct. Okay. So it is indeed a grand theorem, and it's reasonable to call it the fundamental theorem, because at once then it suddenly we see and we can understand exactly what the possibilities are for finite abelian groups. And it gives us a good systematic way of understanding what they are. Now, what we're doing in chapter 13 is approaching the proof of this. One immediate, we did look at this last time, but if we just look at this example 13.5, so for instance, 13.5 considers, so for instance, finite abelian groups of size 540. Remember, what's the size of this thing? What's the size of this thing that I've written down? How many elements here in this group in total? Well, it's a direct product. And a direct product of groups on a set level, it's just the Cartesian product of these sets. And how many elements in a Cartesian product of sets? Well, there you're looking at all kind of tuples you can form, taking one element from each set, putting them together in order tuples. So the amount of things in a Cartesian product of sets is just the product of the size of each set. Okay, so the size of each set, or the size of each group there is this index here, the power of the prime. So this thing, the size of this thing in total is just the product of all these prime powers. Okay. So we can understand this example then. What are all the possibilities for the isomorphism class of finite abelian groups of size 540? Well, we base it on the prime factorization of 540. 540 is 2 squared, 3 cubed, 5. So the possible direct products of cyclic groups we can have, because when you multiply together their sizes, it must come to exactly this. The possibilities are just the different arrangements and the different ways we can accommodate cyclic groups of sizes a power of 2, a power of 3, and a power of 5. Okay, and you can only have at maximum 2 2s around, 3 3s, and 1 5. Okay, so you just look at the possibilities. You can have them all spread out fully. Z2 plus Z2 plus Z3 plus Z3 plus Z5, all spread out as much as possible, and then you can have them all collapse together as much as possible. So I've done this somewhat systematically. So the last example is Z4, Z27, Z5. So that's your 2 squared, your 3 cubed, and your 5. And then the other possibilities are just the intermediate ones, where some of the Some of the prime factors are gathered together and some still separate. Okay. So you see, you've only got 6 possibilities. So it suddenly, really limits the number of possibilities for different finite abelian groups of size 540. It's quite a small number of possibilities, really. Groups of size 540, there's potentially a lot of rich structure there. And of course, in non-abelian groups of size 540, there'll be vastly more than 6. Okay, I don't even know. Yeah, we probably don't. But I have to look up, but a huge number of non-abelian groups, I expect. But for abelian ones, because the operation is commutative, it severely limits the potential structure there. So there's only 6 different times. Okay, now, not surprisingly, the proof of this, isn't just a simple 1-paragraph proof or anything. It does take a bit of approaching and to set up some intermediate results. But the kind of common flavor to all the arguments is talking very carefully and going back and forward between the size of a group or related groups, subgroups, and the orders of elements. Okay, because that's what it's all about. Because especially if we're on our way to showing that the thing is a direct product of cyclic groups, well, cyclic groups have generators, and it's the order of those elements, the order of the generator, which gives you the order of the cyclic group. Okay. Remember, we're using order to very slightly different ways. The order of a group is simply the number of elements in the group. The order of an element is the number of elements in the cyclic group generated by that element. So it's the smallest exponent such that, the smallest positive exponent such that that element to that power is the identity element. It's the size of the cyclic group generated by that element. Okay, so the way it approaches is we start to talk about P groups. Okay. I'm falling into the trap of giving the previous lecture again, but I'll avoid it right now. So P group G is one where all of its elements have order a power of P. Might be a different power of P for different elements, okay? But if you look at all the elements in the group G, every element you see in there has the order of that element is going to be some power of P, okay? That's what's called a P group. And this is going to be, we're going to base the fundamental theorem on this idea, and we're going to prove it in a kind of an induction type argument. Now, last time what we spent, the major piece of work last time was improving lemma 13.6, which said that if the order of a group was n and P divided n, okay, every time I write P is reserved to talk about primes. So this is quite general, it applies to any kind of group. Just if P divides the order of a finite abelian group, of course, all the groups are finite abelian here. If P divides the order of a finite abelian group, then G contains an element of order P. We proved that last time by doing a careful induction argument on the size of the group. Okay. I won't say any more about it now because we spent our time on that last week. So the next lemma is, you can appreciate how that's a result which is talking about the link between the size of a group and the order of elements in the group. If the size of the group is a multiple of a certain prime P, then somewhere in that group there is an element of order P. Maybe more than one, but there's at least one. So 13.7, so here's where we start to talk about P groups again. So a finite abelian group, that kind of goes before everything in this chapter. A finite abelian group G is a P group. And a P group is one where every element has order some power of P. A finite abelian group G is a P group if and only if the order of G is some power of P. So again, this is a result which is drawing connections, specifying connections and describing them between the size of a group and the orders of elements inside it. Okay? So the P group G, as we said, is one where every element inside it has order some power of P. And now we're talking about, well, if that's the case, that's exactly the same as saying the order of the group is a power of P. The size of the group, the count of the total number of elements in the group, is itself some power of P. Okay, this is an if and only if, so it requires a proof in two directions. First of all, we'll assume the order of the group is a power of P. So now we want to prove it's that it's a P group, that every element in it has order some power of P. Well, by Lagrange's theorem, or it might have even been a corollary that we called Euler's theorem or something, but the basic idea, for every element G in the group G, when you raise G to that power pk, it must be the identity element. Okay, because if you focus on any particular element, you can talk about the cyclic subgroup generated by that. By Lagrange's theorem, the size of that cyclic subgroup has to divide the order of G. So it must be a divisor of P to the power k. But a divisor of P to the power k, must be just some lower potentially power of P, so that in this power here, G to the power of P to the k, in there is already G to the power of its own order. Okay, because that's some potentially smaller power of P. So that is equal to the identity. So, i.e., the order of G. Some books use, for the order of an element, some books use O, a function O of the element. But Judson uses kind of absolute value signs to talk about the order of an element. So you can use those. P divides P to the k. So the order of G is a power of P. Okay, because the only things that divide P to the k are other powers of P. Yeah. So this is talking about every element in the group G. So every element in the group G has order a power of P. So in other words, G is a P. So that's the definition of being a P group. So that's one direction. That says if the size of G is P to the k, then it is a P group. Every element in it has order some power of P, smaller power of P perhaps. To go the other direction, we have to show being a P group implies the size of the group is P to the k. But we'll do that doing the contrapositive. So we'll say if the order of G is not equal to pk for some P, that means, i.e., there exists a different equal to P, and Q divides the order of G. That's the only way you can not be a power of P. The only way to not be a power of P is to be divisible by some other prime. So if there aren't any other primes that divide you, that means by definition you're some power of P. So there's some other, if we assume that the size of G is not a power of P, means there's some other prime floating around that divides the order of G, but the the time we spent last time then, lemma 3.6, 13.6. If you've got a prime dividing the size of the group, that means within that group you will find an element whose order is that prime. So G contains an element of order Q. Well, if it contains an element of order Q, it's not a P group. Because being a P group says every element has order of power P. So G not a P group. Well, that's the contrapositive of the other direction of the result we're trying to prove. So if not being size a power of P implies not a P group, that means being a P group implies your size is a power of P. Okay? The contrapositive of that says that G a P group implies the order of G is P to the K to some K. Okay. So that's good. Again, strong connection between size of the group and orders of elements. Okay. So you're a P group, you contain things which have order only powers of P. That means the size of you, the size of that group, is itself a power of P. Okay, so good, strong connections between orders of elements and the size of the group. Okay, now the fundamental theorem of abelian groups says, effectively, that you can break down any, you can express any finite abelian group as this kind of direct product. Well, as a stepping stone to that, we're going to show we can take any finite abelian group and express it not yet as a direct product of these cyclic groups, but as a direct product of P groups. So we're kind of breaking down G into a direct product at some kind of intermediate level between just knowing G on its own and knowing G as this full kind of canonical direct product. And that would be a stepping stone to the main result. So this is theorem 13.8, lemma 13.8. So we'll just take a moment to theorem. This lemma, I think there's something missing from the proof of it. So which I know how to fill in the gap. So I might need to communicate with Tom to suggest an improvement to the proof of this. But let's take a moment to understand the statement. So, okay, let G be one of our objects that we're studying, a finite abelian group of order n. So the size of G is n, and okay, we want to talk about the prime factorization of n. So we understand well from last year, any integer at all can be written uniquely, essentially, as a product of powers of primes. And sticking with his notation here. So the size of the group n, we look at its prime factorization. We indicate the different primes that feature in the prime factorization of n. So those are P1 through Pk. Now these primes are distinct, which is just these Pi are distinct. Just slightly confusing. When we reach the final form for the finite abelian groups, you can see the same prime appear in a number of different cyclic groups, same prime, but here these are distinct primes. So the conclusion then says G is now it's an internal direct product. Remember, internal direct products and external direct products, they're very closely related. This means we're going to effectively build an isomorphic version of G as being a direct product, for the different things in the direct product are all different subgroups of G. So therefore, it's going to be an internal direct product. So you're building up the direct product using subgroups of it. So it's going to be, G is going to be, when you're doing an internal, you can write it effectively as just the product of these sets. So each GI is a subgroup of G. For each GI, I'm adding a bit to the statement, is the GI, these are called primary components. Okay, he doesn't use that terminology, but you'll see that terminology used elsewhere, i.e. GI consists of all elements of G whose order is the power of this prime, of the ith prime. So associated to each of the primes that feature in the prime factorization of N, we associate the primary component corresponding to that prime. And the primary component corresponding to that prime is a P group. It's the group consisting of everything from G whose order is a power of Pi. And we know that these are all non-empty. These are all non-empty. You know, these things do exist, because the previous lemma, 13.6, said if you have any prime that divides the size of the group, there's at least one element, two at least, it and its inverse, but there's at least a few more. But there are elements in the group whose order is that prime. Okay, so there are certainly floating around in G, in this G, there are elements of order P1, there are elements of order P2, and elements of order Pk, and so on. So these primary components we're defining here actually do exist. There are things in G. Okay, well, I've just defined G on a set level, where each GI is a prime, and GI, I mean, what's implied here is that GI is a subgroup of G. The internal direct product construction only refers to subgroups. So for this lemma, okay, it's stated a bit more tidily in the notes, but you could add in the terminology primary component of the GI in the notes. So that's an internal direct product. So in effect, this is going to say that G is isomorphic to G1 cross G2 cross all the way up to GK. So first of all, this lemma, we're going to have to prove that these primary components actually are subgroups, so it's not too hard. But then prove that G is the internal direct product of those. And that involves, we have to show that the GIs are all distinct as much as possible. Now, how distinct can subgroups be? Subgroups, they can't actually be disjoint, because any two subgroups always share one element, which is that. The identity. The identity. Good. So you can't have completely disjoint subgroups, but up to that you can. So you can have subgroups which are distinct as much as possible in that they only have the identity in common. So, and that's what we require for this internal direct product construction. That the groups you're using share nothing in common except for the identity in a pairwise fashion. So we have to prove that. That's a lot of the time taken to prove it, and then finally prove that when you do this internal product construction, that you get all of G. See, we're not claiming here that G. We're certainly not claiming that G is the union of all the GIs. It's not the case that the GIs give you a partition of G or anything. That's not the case. But the GIs kind of separate off special elements of G, elements whose order is just a power of a single prime. See, in general, because the order of G is the product of these prime powers, in general, for a random element of G, if you just pluck random an element out of G, what would you expect its order to be? You'd expect its order to be some divisor of N. So typically, you'd expect to see a few different primes in there, in its order. A few of those primes raised to powers less than the alphas, okay? Because the order of the element has to be a divisor of this. If you just pluck something random out of G, you'd expect a few different primes there. So the primary components are kind of special. They just separate out the elements whose order is a power of a single prime. And that's by no means all of the elements in G, certainly not. But they're special in that you can generate any element of G by multiplying together one element from each of the primary components. Okay? So that's something we'll have to prove, that will be required to prove. Okay, well, in this afternoon session, we'll prove 13.8. Okay, so it's a detailed argument, so we want to take our time with it. And indeed, I think there's something extra that we need to supply to the argument in the book. But just in the final couple of minutes, we'll just kind of indicate how the argument works then to get to the fundamental theorem. So the fundamental theorem is looking for something like this expression here. Just probably wrote down at the notes at the start. Okay, it says that G is going to be isomorphic to something like this. So 13.8 is a stepping stone. It's going to say G is isomorphic to a direct product of groups. But the groups, each of the groups in this direct product are P groups. They only contain elements whose order is a power of the same prime. Okay. So then the next lemma, 13.9, the next lemma just focuses on a P group. So it's just going to focus on one of the groups in this direct product construction. And in 13.9, we're going to prove that one of these special P groups, this is a group just consisting of elements whose orders are all powers of the same prime, that group splits up into a direct product of cyclic groups. And we do it by induction. There's an induction argument that says if you take any P group G, so this is lemma 13.8, any P group G, you will always be able to say it's isomorphic to, so this is what the lemma 13.9 will say, that there exists some element, it's a special element of G, it's an element in fact of maximal order in P, but that's a detail which we'll come to. But there's some element to be found in G. If G is a P group, which each of those GIs are, P group for different primes, focus on one of them, there will be an element there such that you can separate off a cyclic group generated by that element. Now it's a P group, so its element will be a power of some prime. So this group here will be isomorphic. It'll be a cyclic group of order some power of P. So it'll be one of the Z P alphas. But that's not all of G. There'll be a direct product to using some subgroup H of G. So in effect, this will be another internal direct product construction. So focusing on one of those factor groups there, those GIs, we'll have an argument that we can always separate out a cyclic bit from one of the GIs. But then you see this subgroup H will have size strictly less than the size of G. And H will be a P group again of G, so all the elements in H have order of power of this prime. So this lemma can apply inductively to show that we can keep separating off out of G and then out of H in turn, keep separating off cyclic factors. And if you can decompose any GI, any one of these GIs into a direct product of cyclic factors, then you can decompose the whole thing with different P groups here. So that's kind of a look ahead to the steps to come. So we've got two substantial pieces of detail to prove. First of all, that we can achieve this isomorphism. That's lemma 13.8. And then 13.9, that we can start chopping cyclic bits out of each of these. And then by induction, that can be completed to give some kind of expression like this. Okay, so I'll pick that up this afternoon. That's okay.